All right, everybody. So let's talk about how water moves around in lakes, right? So there's a variety of different ways in which water moves. And the first one I want to talk about is called a lake seish, okay? That word is seish. And this is what happens when you have a long, consistent wind, okay? And essentially, if you have wind here coming from the left, going to the right here, what happens is it stacks essentially water up over here. Now, we don't think about this as like actually happening and visible, but it's actually a really cool phenomenon. If you have, I mean, you need like wind for a long time, like a couple days going in the same direction. It has to be consistent at a pretty high level, right? Because what we're thinking about is stacking water, and gravity is, fighting against this, but that wind can overcome that. And what happens is when the water or when the wind goes away, it needs to reach an equilibrium. So it's kind of like a seesaw then that goes back and forth and back and forth, right? So all of this stacked up water will move to the left, and then it'll, it'll be up like this, right? So the water will be all in here, right? And then it goes back and forth and back and forth. So this slows down basically, once you get that wind stopping, the seish will go back and forth for quite a while, but gravity and friction eventually slows that down and brings it back to equilibrium. It's pretty cool, though, that these seishes can last quite a long time. Okay, so there's this one seish that was studied in Lake Geneva in Switzerland, and this isn't like a record one. It's just one that's been studied very closely. It was a 1.87 meter seish. Okay, so that's actually like 5 feet of water, rising up on one side, and then it would take 73 minutes for it to basically go to the other side and come back. Okay, so you can kind of like think about this as like put a bowl of water on a table and then bump the bowl, right? And then it just kind of goes back and forth a while. Now, in that bowl, it settles down within 30 seconds or so. But think about the huge mass of water. Lake Geneva in Switzerland is huge. Even just a small lake, if you have even just like a seish that is 1 foot tall, that's a lot of weight of water that is stacked up on one side, and it's going to take a while for that to go down. So after 2 weeks, the seish was still greater than 10 centimeters tall. So, it takes quite a while for these seishes to go away. Now there's this other crazy thing that can happen called an internal seish. Now what's interesting is external seish is so this is an external seish here, due to like actual water level here. But an internal seish is something that happens due to stratification. So you have the same kind of wind that will, let's say the wind is coming from this direction, right? And what it does is rather than, so internal seishes and external seishes can happen at the same time, but they don't necessarily have to be in sync with each other. Okay, so what happens is rather than the water just like stacking up like this, what it happens is the stratified water, the less dense, warmer water, stacks up over on the right side. So we see here essentially the metalimnion is deeper on the side of the wind, or on the windward side, or the leeward side, sorry. So the wind, goes to the right here, and on the right side of the lake, then you have this stacking of warmer water. So it depresses that thermocline, and when that wind goes away, then this needs to equilibrate, and it creates this weird sort of wave inside the water. I'll have to link. I'll link to a video of showing one of these in like a little aquarium, because it is pretty cool to see. You can actually replicate this relatively well just in a small aquarium. And then this wave will bounce back and forth for quite a while. I've done it in the lab where I can get it going for several minutes. And what happens is this wave is actually a lot slower, right? Because it's density differences in the water that are driving this, and the differences, the gravitational difference between the weight of the water of stratified versus of the stratified water is not that much. So it's very slow acting. So when we think about this internal seish, then what we can see then is, oftentimes the hypolimnion down here has more nutrients. So the nutrients can get moved up into the limnetic zone due to these waves, right? So over here on this side, the hypolimnion is, this limnetic zone over here is being exposed to the hypolimnion. Now, and there could be some nutrient fluxes there that wouldn't be caused if you didn't have an internal seish. So let's now think about what happens when you have a mixing lake. And what we're going to talk about is like a dimictic lake, like a normal Wisconsin lake, and it's going to be a stratified lake that, mixes in the spring and the fall. So remember, depending on where you are in the world, these things can act differently, but I'm just going to talk about it for a generic lake. So I think the best way to start talking about this is first talk about all the different types of lake mixing, okay? And then we'll get into this seasonal mixing pattern that's common in Wisconsin lakes. So, an amictic lake. Mictic refers to mixing, and A means no. So, a lake that doesn't mix. So, there's this really cool lake in the middle of Antarctica, and it's 2 miles underwater, or under ice. And there's this like pretty salty water that has it is not heated via transmission through ice. There's some like lakes in Greenland where this happens, but Lake Vostok itself does not get any light heating it. So yeah, so first off, when we're talking about lake mixing, let's talk about an amictic lake doesn't mix, okay? A cold monomictic lake then is essentially, think about a lake way up in northern Alaska or northern Canada, and could be at the top of a mountain. Essentially, it's frozen all year round except for a little bit in the summer, and the lake just pretty much gets to 4 degrees Celsius, and then the wind can mix it. Okay, so it's just during the short summer you get a small mixing period. So monomictic mixing once a year. Dimictic lake is probably the most common lake, just because this is where these are most of the glacial lakes in northern hemisphere. This is what's going to happen. So cold temperate regions, basically think of like middle Illinois and up north, up to pretty much northern Canada. You can get a dimictic lake at high altitude in the tropics. So during these mixing times in the spring and the autumn, you don't need that much wind because the lake is all at 4 degrees Celsius. The lake can mix relatively easily. But when there's ice over the top, you're not going to get any mixing. And then when you have that strong thermocline in the summer, you're not going to get any mixing. So that's why we call it a dimictic lake. It mixes twice a year. Okay, a warm monomictic lake. Think about a lake maybe in the middle of Oklahoma or the middle of Arkansas. Okay, essentially what you have is, rather than it's like 2 seasons, right? A very long summer that the lake is stratified for most of the year, and then during the winter, maybe December and January or something, January and February, the lake is the entirety of the lake then is 4 degrees Celsius. So you get, mixing over the entire winter for several months. Okay, so coastal regions of the U.S., the southern U.S., parts of Europe will have warm monomictic lakes. Polymictic lakes, then, these are lakes that mix all the time. So this might be a lake where you get heating, a shallow lake right here, where you get infrared transmission to the bottom of the lake essentially, and then you don't get any stratification, so the lake can mix pretty much all year round. Oftentimes maybe the lake is just shallow enough that or warm enough that it doesn't really get ice cover, and you just get sufficient wind mixing up the whole lake. These are common in the tropics, and basically most wetlands would be kind of considered like this too. So when most people think about water movement, they think about surface waves, but realistically, surface waves don't really do much. Okay, these are wind-driven movements of circulations. Basically, these it just moves the very tippy top of the water in these little circulations that are only like real short movements. They don't get to the bottom. They're certainly at the metalimnia, they're stopped. So really they're only limnologically important at the shoreline. So what happens is you get wind going in one direction, blowing the water, starting to move these water in these little circulations, and then what happens is you see these little circles here. This water moving in this direction will then, these arrows are actually incorrect, but it'll then, so if this one is going counterclockwise, this one will go clockwise and then counter and clockwise. So they'll like drive each other and spin each other, and as those little circulations stack up on top of one another, we get basically the waves, the circulations in sync with one another, and we get these surface waves. Now, if you have strong enough wind, essentially what happens when you get whitecaps is the wind is strong enough to just basically blow the top of the water off, and then it collapses down. So what happens when you have breaking waves at a shoreline is that these rotating circulations essentially stack up on top of each other, right? So before it was down to the metalimnia, and now you have only, this much water in which to house that same circulation, so it gets taller, and the wave stacks until it can't support itself anymore, and then it breaks and falls down, at the shoreline where surfers are. So whether we're talking about an ocean or a lake, same thing happens. Ocean just happens bigger, right? So surface waves, their heights are more dependent. Yes, it's dependent on the amount of wind, but it's really more important the length of water that the wind has time to act on it. Right? So, if you have a 20-mile-an-hour wind going this way along the length versus the width, if the wind was going this way, there'll be bigger waves over on this side, as opposed to if the wind was going this way, right? Now, that's maybe not unsurprising, but what I do want to say is, like, if you were to have like a 30-mile-an-hour wind going this way and a 20-mile-an-hour wind going this way, these waves would still be bigger because it more depends on what this thing called fetch. The fetch is the distance over unbroken water in which the wind has blown. Okay, so usually when we think about the fetch of a lake, we think about the longest distance that you can make. So this is Lake Koshkonong over by Fort Atkinson, and the fetch is somewhere like that, right? And there's an 11-kilometer fetch, And when you put this this equation, this h is talking about maximum wave height. Okay, so what Lake Kashkanan with an 11-kilometer fetch, if the wind was going, in this direction, what height of waves would you have over here hitting this shoreline? And this is like maximum wind. Say let's have like a 70, 80 mile an hour wind. What would happen? And what we would see when you put this 11 kilometers in here, remember you need to have 11 kilometers, but put it in centimeters here. Take the square root of 11 kilometers in centimeters times 0.105, and you get a 1.1 meter wave. Remember, you need to, but this height will be in centimeters, so you have to convert back. So you might say, well, that's only like a 3-foot wave. That's not very big for 11 kilometers. And, that's true, but you just can't really get waves much bigger than that. So Lake Superior has the largest fetch in the world. It's for lakes, right? So the largest fetch is 430 kilometers. And you can get essentially 7-meter waves that are 22 feet tall. Now, there have been bigger waves reported in Lake Superior, but that's due to more wave interaction and not just wind driven, right? So if waves can get stack up on top of each other and create these rogue wave kind of scenarios that can swamp boats, and these often get reported in the ocean by ocean liners and things. But if you were to take the Pacific Ocean and put 100-mile-an-hour wind going across the Pacific Ocean, what you would get would be a 32-meter wave, 106 feet tall. And that's probably about right of the largest waves that we can get. You just never really get 100-mile-an-hour wind consistent blowing all the way across the Pacific Ocean. So you don't find waves like that very often. All right, one of the last things I want to talk about are Langmuir cells. Langmuir cells are these weird type of waves, circulations that on a windy day go to a lake, and you'll see these lines. You can see them here. And these lines what they are these circulations. So if the wind is going this way, it creates these weird circulations, okay? And what you get is a conglomeration of bubbles. So this one will go clockwise here, and the one over here will go counterclockwise. So what it does is it brings up bubbles and algae, and they get stuck in here, and because those bubbles are floating, and then they don't get pressed down with these circulations. So the cause of this is actually not really known, and it's just kind of a mystery that we don't really know why they happen. We can't really model it. But I've seen it. Go to a lake, drive by a lake, you'll see it all the time. They're actually very, very common. And so for when you're thinking about sampling zooplankton or phytoplankton or something, oftentimes you can get really weird samples if you're sampling on a windy day, because if you pull your net through one of these conglomerations of bubbles, right here, right, you'll get an overrepresentation of the plankton in that situation, because they're trapped in these little lines. They're also not directed directly with the wind. They're about 5 or 15 degrees to the right of the wind, and that's due to the Coriolis effect. Oh, sorry, there was when I was talking about plankton that they can get stuck in here. But then the predatory zooplankton are really interested in these areas because they can get a concentration of food and that can't get away from them, and they'll really chow down on these areas. Okay, so the last thing I wanted to talk about was tides in lakes. Everybody always wonders, do are there tides in lakes? And the answer is yes, there is tide in every lake. There are tidal forces going on in your body. If you put your right arm out and your left arm out, there will be tidal differences between your right and your left arm. Now, there's tidal forces between the Earth and the Moon, and the Earth and the Sun, and the Earth and Jupiter, and Earth in the neighboring galaxy. The thing is, the Moon has the overwhelming biggest effect on the tides. Okay, so the Moon is about 2/3 to 3/4 of the tidal forces that happen on Earth. The Sun is the second, and then everything else is really essentially non-existent. But even when we're just talking about the Moon and the Sun, we might as well just be talking about the Moon, because that's the main driver here. But that being said, even the largest lake in surface area, and what you need for tides to happen is a big differences in area, so the biggest lake, Lake Superior, it only has a 20 millimeter tide, so that's 2 centimeters, right? So that's wholly overwhelmed by seishes, barometric changes, all sorts of things. Any type of surface wave will totally overwhelm that, right? So, ecologically, totally unimportant. But when we think about tides on, the oceans, obviously these are extremely important. So let's talk about why we see tides the way they are. Okay, now what happens is, think about the Moon. Okay, the Moon is pulling on the Earth, and it's pulling on the water around the Earth. So let's just pretend right now the Earth is a ball completely covered in water. Okay, and if that were the case, because the water, right here is closer to the Moon than the Earth, there's a stronger pull of gravity on the water and than there is on the Earth. Now let's pretend that the Earth is a completely rigid ball that doesn't flex, even though it does. As the Moon, goes around, there's actually tidal in the Earth's rock and core and all that stuff. But let's just say it's a completely rigid rock. Okay. So what happens is you can draw gravity vectors. So the gravity vector for water is going to be essentially longer. So the longer it is, the more effective gravity. And then the Earth one, let's put the Earth one right at the surface of the Earth. That is then shorter. So what you can do is draw a line to the net vector will be, the net movement will be from the top of the Earth vector to the water vector, and then you get a net pull. Okay, so you get a net, the net movement here, because the Earth is moving this way, I should say the Earth is accelerating that way, the water is accelerating that way, so the net acceleration then of that water is this much, or whatever the bulge of that water is. Okay, and that's a more complicated explanation. Easier explanation is that the Moon is pulling the water more than the Earth, so it bulges out. And that explains this bulge relatively easy. This bulge is a little harder to explain, right? So what's actually happening here is the Earth is being pulled away more than the water on this side of the Earth. So this bulge on the other side if you draw those gravity vectors again, you get a net outward bulge because the Earth is going, longer accelerating to the right, and the water is going a little bit to the right. So you get a net vector going to the left here, and you get that bulge. Then you might ask, well, why do you get a compression on the sides where the Moon, perpendicular to the Moon? I'm going to try to draw this over here a little bit, maybe more drastically. So, let's say here is the bulge of water, and here is the moon, right? Okay, so draw the gravity vectors again. Let's say that the Earth moves this far, and then this water, since it's the Earth is getting affected, in the middle of the Earth, but then this is experiencing that same, because the Earth, we're remembering that as a rigid ball. At the top of the Earth, then you get the equal gravity vector from the center of the Earth, and then at the edges here, this gravity vector is actually going to be put like a little bit down to the at an angle. Okay, so when you put those gravity vectors together, let's just do it down here now. So this, and then like that, with the same, essentially the same length, since they're the same difference. You draw a gravity vector from the Earth to the how the water is moving, and you get a line here, in this case going up, and then a line here, this case going down. So you actually get a compression where it is perpendicular to the moon, essentially. So you might be wondering, well, given this model, the tide should be the same in every portion of the Earth, and essentially, because there's local conditions, shorelines that funnel water in different ways, we can get huge differences of tides where, around the tropics it'll maybe only be a couple inches of tides in certain, islands, but in the Bay of Fundy in Newfoundland you get like over 20 feet of tides, and it's crazy. But again, in lakes we don't have tides that just aren't important. All right. With that, see you later.